Okay, so hello everyone. Aziz will present today about the category of bundle scenarios for simplicial complexes, right? Okay, Aziz,
Thank you.
you can take away. Yeah.
Thank you. Okay, of simplicial complexes. Actually, we will have two talks because we will continue after that for simplicial sets, and this is the goal to do this for simplicial sets. So I want actually to start from the simplicial distribution approach, okay, that use simplicial sets, and to present the goal, what is the goal, and what we feel like there is something that we can do there. Even with all the flexibility of this language, there is two things I would want to talk about this that we need to extend in order to do this. First of all, like in the simplicial distribution approach, we have the following. First of all, we have like a uniform outcome, number of outcome for all the measurement. We have uniform number of outcome for all the measurements. Like if we take this to be our outcome space, delta z m, so that the vertices of x, like x delta z m, then the vertices of x are the measurement. So we already like fix that there is m outcome. But sometimes we need to extend this language in order to get like a different outcome, different number of outcome for different measurement. Okay, so this is one goal. Like we want this, we want to extend the language in order to be able to be able to let's say, okay, to have like different number of outcomes for every measurement. Yeah. This is one goal we want. The other one, it's about morphism between two scenarios. Like we know that we already used it, that like, for example, by the collapsing that we have something like some simplicial set map between two measurement space. And then this induce from simplicial distribution x delta zm. This is contravariant. Yeah, it will be like this. Yeah. Yeah. So maybe let's write it's prime x and then this will be x. We have something like this, then we will have this. And if we have also between y and y prime here, this one. then it's induce simplicial distribution from, yeah, this also can be any y, right? It's not have to be like delta of Zn. Yeah, it can be any y, fixed y, okay, outcome space. And here also it's like can be fixed, some fixed measurement space, and this induce this map x y prime, right? And maybe one can say, okay, so we have like, what is the map between measurement space? It's like two maps, like one map, let's call this F, and let's call this G, like a map between this from, let's say, xy to x prime, y prime. It's these two maps, okay? Like F and G. One can define like this, it's okay, but what is we have here something like it's separated, like, okay, this will induce like this two maps, one map from x prime to x and one map from y to y. This induce simplicial distribute from xy to, which is the composition like what we have yeah, here, something like the composition of such a map. But we see like it can be separated, like one for the outcome and one for the measurement. But sometimes we need something that mixed between the things. Okay, we'll explain later what we mean by mixed. Like some, but like some maps that it's not something like separated. Okay, some map for outcome, some map for the measurements, and then we got this map between them. We want something that depends which measurement. If it's for this measurement, it will be another map for the outcome. We want something mixed. So by this approach, we don't have when we look it's like this. So it seems like we need even the language to be like to mix the outcome space and the measurement space together in some way. Okay, we will talk about it later, but this is two problems that or the two things that we don't have really in this when we talk about simplicial distribution approach. And later at the end of the next talk, we will see that we will solve this problem by introducing the extending approach that extends this, the bundle simplicial, bundle simplicial approach, let's call it. Okay. So let now do this. I want to start from like where it people first start to do this in the sheaf-theoretic approach. They start to think about morphism between. They actually extended to be outcome. This one they extended like because if someone, I will now I will back to this language, but if one can look at the first paper of the sheaf-theoretic approach to contextuality. So you will see that there was really fixed one outcome, but later they solve this problem, and also they also have this morphisms between scenarios that mix not like this. Yeah. Okay, so let's start in the by the sheaf-theoretic approach. I can remind you what is. I don't know if we talked about it. Did you talk about this at the beginning, Cihan, or I don't remember? In your first talk, you started with this, or you were just
Yeah, I talked about sheaf.
You talk about this. Okay, so let me,
but not in the bundle picture, right?
Yeah, not the bundle. Yeah, but as a sheaf theory, yeah, it's good.
Yeah.
Okay, let's start about this. Like what it's using the language of simplicial complexes. So they said, okay, we have like the scenario, how we can say how the measurement, how the context in the measurement, which measurement we can do together is by there is a simplicial complex that tell us this. And there is outcomes like this simplicial complex, and there is like, of course, the vertices of this, let's call it, how we call this, like in the languages I did. Okay, let's call it, this is the vertices. I mean here the vertices of this. Okay, this will be the measurements. Okay, the measurements. And here the complex, like everyone, this is context. every simplex in sigma is context. And here we have O. What is O? O is it's set for every x, for every measurement, for every vertex in this sigma, okay? So this is a scenario for us. Here is like the measurement space, like it's not a simplicial complex, and here is the sets. Okay, it's a set for every measurement. So we see like here it can be different, like for every measurement, different number of the how many like member in OX, it's different from X to X, can be not the same. Yeah. So we have this language, and actually we can like instead of writing like this, we can write it by one functor. Which functor? Like this functor that going from, because first of all, every simplicial complex, we can think about this as a category. C sigma, what we mean by this category, the object of this category are sigma, like object of this category are sigma on sigma. This is object of this category. And morphisms, when we have some sigma like that with inside sigma, this is morphisms, how it looks, okay? Morphism. So it's really a category, this give us a category, and we have this map, or this functor, sorry, from this category to set. And they use this notation, I think, for this functor, because it's give me the outcomes, like what it's give me, like for sigma here, for object sigma, it's give me this product. Okay. So one can think that this is the scenario, by the way, this morphism is a scenario, okay? Like, because inside this morphism, we have all the information. We have the set of outcomes, like one can go by x, it will give me OX, okay? So we can get the outcome by this functor. And we can like back to if we know the vertices, maybe we need to know the vertices, I think also. If we know this, what is the measurement, and we know the functor, we can really like know what is the simplicial complex here. Yeah. So we like, yeah, collapsing the information all in this functor. Okay. Now how they defining joint distributions? Like they called it empirical model. We called it simplicial distribution, like a joint distribution, when we have some distributions that join together. The easy way to do this is by using this functor, actually. If we take this functor, okay, that give me the outcome, and then we apply the distribution functor, yeah, and then we take like this composition, and some empirical model or join, it's something in the limit of this, in the limit, okay, limit over this, like this is our diagram. Because what is this actually? Something in the limit, like it's give me, for example, for this sigma, like let's say we have sigma 1, sigma 2, sigma 3, and they somehow they have here the sigma 2, sigma 3, and here I don't know. Okay, let's say two of them. It's easier, even. Yeah. So what we have here actually in the limit, something in the limit, we apply on this diagram, like this. Let's say this is our C sigma. Okay, this one is our C sigma, and we apply first of all this one. Like we take this, by the way, is contravariant factor. Maybe I didn't explain this, that it's contravariant factor because you imagine like if this is the map, like here I apply this one, so sigma, why sigma 2, sigma 3, it's okay. Anyway, sigma 2, so actually all the outcome of this, we have the restriction to this one, to the let's call it tau. Yeah, the intersection between them. Yeah, it's obvious what was the map between here and here. And we have also this map, sigma, sigma 3, yeah. And then we apply D. We apply the functor D on this diagram. And something in the limit. What do we mean something in the limit? It's mean joint distribution, right? The distribution here and distribution here, that restriction is the same. Yeah. This is what we mean something in the limit. And you can imagine if we have all this, all the simplices inside sigma that give me the context, how is the context matched together. So something in the limit is like joint distribution. So they call it empirical model. So this will be the limit of this. This is called the empirical model for this scenario. Yeah. Okay. So this is the language, and now we let's go and see it's how they define morphism between two scenarios. Okay, how they define morphism. Of course, at the end of the day, why we need also morphism, because it's this morphism act on the empirical model or joint distribution or simulation, like in their language, like yeah, they act on this, and we get the what called like simulation. Okay, we'll talk about this later. So how they define it? First of all, to define it, I need to define for you what it's called the relation, simplicial relation. Yeah. Now it's what we start like morphisms between between scenarios. We call it standard scenario. What we mean standard scenarios, we mean like this kind of scenarios in the sheaf-theoretic approach. Okay, so definition, simplicial relation, yeah, simplicial relation from sigma to sigma. Like I have two simplicial complexes. Simplicial relation is a relation. What does that mean? Like is a relation here, like pi inside sigma relation, normal relation, but it's simplicial also. What does that mean? That it's simplicial such that for every sigma, okay, let me remember, I forget this, yeah, for every, for every sigma, let's try sigma prime, pi sigma prime, it's in sigma. Yeah, but what we mean by this, let me say what we mean by this by sigma. Yeah, we mean by this is here, but by sigma, like every 1x in sigma 0, such that x, there is someone y, let's say in sigma here, and such that this in the relation yx in the relation. Yeah. Like the image, if because the relation it could be a map, then it's the image. But this is like generalization of the image. Yeah, but it's by sigma. How you can imagine, right? Right. It's like every thing here that have someone from this sigma. Yeah, with them. It should be here. Yeah, everything's here that have someone in the relation. Yeah. This is the definition. Like if it's a map, then it's a normal, it will be normal map. Like this is the image. Maybe I should call it 6 and this is y. It's better. It will be yeah, maybe x this y and this x. It will be like more make sense because it's like a map. Like where we are. Yeah, we like to call it y. And this x. Yeah, there is x. That fx of y is an image of this. It's y. Yeah, this should be in sigma. Yeah, should be in sigma. This is the conditions that it's have in order to call it simplicial relation, not any relation. Simplicial relations that it's preserves this the simplicial structure. Yeah, simplicial complex structure. Okay, so something important here to know that this actually pi a relation or a simplicial relation induces a functor between the corresponding categories. Right? We say that we can see this as a category, right? We can see as a category, and if we know it will be the minimum. We can know the first object, like it will be the vertices. So we have, so we can imagine how it's look like, right? Like by this pi sigma, like every sigma going to pi sigma. And let's call it pi like this sigma. We can call it pi sigma prime. Okay. Now we can define what it's meaning morphism between two standard scenarios. So definition. Given scenarios or standard scenarios, sigma yeah. A morphism pi alpha from this one to this one is simplicial. It's two things like pair. A simplicial relation pi. We have to be careful here. Pi from where to where? From sigma prime to sigma, right? Simplicial relation pi from sigma prime sigma. And what is alpha? Alpha actually it's a natural map from this functor. Like we have this is sigma, we have this pi, right? We have a functor like this, and then we have this the functor the functor of outcomes. Like let's call this for this scenario. And alpha is a natural morphism, natural map from this to the functor that corresponding to the sigma prime. Yeah. Yeah, this one. Okay. This is what that mean. It's of course like from the definition one can see that really it's not something that as we said before, it's not something for the measurement, some map for the measurement and separated in separated way and other map for the outcome. No, here things mix, you see, like because of really we do the composition like this one, right? This one for the measurement, right? Like one, I will explain the definition, but even without explaining, by seeing this, we see that there is something that mixes this map. We can define the map between the outcomes, like here, this map between the outcome, but without involving pi. Like it's, yeah, everything is depend on this pi, yeah? If there is something that for every, yeah, so this is the game. Like I want, like what I say, the two things at the beginning, actually it's the same things, because the things, it's like to differ between the outcome of this measurement and the outcome of this measurement, not all, but in a good way, like in a good way that preserving the structure, yeah. So here we see like really that we can separate this and say, oh, okay, we have some map, we apply some map of for the measurement, and then we apply some map for the outcome. No, it's together, it's mixed together. So what it say, like they say, like if I have, for example, x here inside, I'm sorry, some x, or even sigma, but let's say maybe it's easier to say we have x inside here. Then this x actually have pi x, yeah, pi x inside, because it's relation, right? Pi x inside sigma, because it's relation. So pi x, it's not a vertex. It's not, because pi, it's not maybe a map. It's a relation, yeah? So pi x, everything that doing relation with x, with relation with x for this simplicial relation. So we have this. And here, then we apply alpha of, then we apply, sorry, this on pi x. So what that mean? That mean all the, I use the same pi for this product and this, yeah, it can be confused, but okay, let me maybe make it bigger in order not to make confusing. And then all the y that in pi x or y, yeah. And actually alpha, it's a map, alpha x, it's a map from this to this one, to ox, yeah, because ox, what is ox? Ox is actually the image of this one, yeah, that, yeah, yeah. So from this to this, yeah. So see, we see for every x, we have x squared, x in sigma, we have such a map, yeah, such a map for every x. But of course, like at the end, this is also good with morphisms inside where inside sigma, like sigma prime, the one that give me the simplicial structure, yeah, of things here. Because not it's only separated alpha x. No, it preserves the structure of this, because it's a natural map, yeah, between functors. So it's also preserving for morphisms. Yeah. So this is what we have actually. And we see like it's something like mixed between, here it appears pi x. So it's for all the outcome inside this to one outcome alpha x. We have many maps that compatible together. At the end, map between outcomes at the end, but what they compatible together with the by the structure, simplicial structure of this. Okay, this is the one, and maybe I need to explain for you some things. I need to explain what that mean, composition, right? And maybe I'm will not really explain this how it's act on empirical model, because we will do this general case, yeah, and maybe we'll delay. But let's say what is the composition here, okay? How it looks the composition, why it's really this morphisms, like what we want at the end. We want this category of scenarios, of standard scenarios, let's call it, where the objects are the object something like it's scenarios, standard scenario, and the morphisms we want to have this as a morphism. But what is the composition here? It's the question one. How it looks like the composition. So let's say we have from, okay, let's write from position let's say we have pi alpha, and so this one, and we have let's say pi 1 and pi 2 beta. So this one. So first of all, we compose these ones, like pi 1. Pi 1 from this to this, right? And pi 2 from this, sigma this to this. So we can compose this before, like sigma 2, and then this. This will be from this to this, right? We need this map from this to this. And then what is I want to now what I need the natural map, I need this, but then I need now, okay, this will be one for the composition, but I need now the natural map, right? The natural map, where the natural map from this, like from this one, the composition of this, but one can see that the composition of this as the composition of the functor, because this is going from this, it's by itself functorial. So going from simplicial complexes to categories, as I explained before, it's functorial. So we can see this as a composition of this. So we need something from this, right, to this. This is what we need to put here, right, in order to be really a map from the first one to the third one, right? A map from here to here. So what we actually doing, like this is p pi 1, and we know that we have alpha here, right? From this to this, we have alpha here. And then we compose, and we have what we have here, we have beta. And then this is only the composition, yeah? We have this beta from this to this, and we compose this. Maybe better to say like, because maybe one will tell me what you compose here. Actually, let's put here the identity from this functor to this functor, the identity of this functor. And then beta will be from the composition of this. It's right, from to this. So let me write it here. We have here some problem with this is with 2 tag. So, sorry. So this is the composition. Let me write it here. So it's like compose first of all this in this way. Because it's like natural, natural morphism can compose. It's like double category. It's not like it's compose what it's called in 2 ways. Like because we're using here the 2 ways because I'm composing alpha. Let's call it like this, alpha and ID for pi 2. Then I compose this composition with beta. Yeah. So this will be the natural map from here to here. Yeah. Okay, so that is the composition. The identity is easy. One can see what is the identity. It's only like this identity to be. Yeah. It's like sigma to sigma is the identities, and it's give me this, and then this also will be the identity natural map. Yeah. Yeah, it's obvious what is the identity, and one can check everything, the activity and things like this. So yeah, this is the composition, but I need maybe to explain you this is why we're doing this, how it's act on empirical model. I will not do this, but one can back to the, it's explained like in the bellboxing paper and maybe in other previous paper. Also in our paper, also at the second section 3, I think it's explained, or 2, section 2, yeah, it's explained there. How it's act, like if I have, this is now like if I have this map, this morphism between scenarios, of course, this give me empirical model. What we say, like this limit, such a the empirical models of this. Let's say we have pi alpha. Yeah, then this will give me here morphism. So empirical model act also on morphism, and this morphism and give us a map from here to here. That means that the empirical model is actually a functor from these scenarios, standard scenarios, to set, but actually it's more than set here. It's a convex set. Okay, maybe at the end we will talk about this. For now, to set, but it's actually we wouldn't prove, but it's the convex set. Yeah, this one. Yeah. Yeah, this is good, but here one can see that there is also a little bit the morphism defined in a not easy way, and really there is a way to improve this. So now we are going to the bundle where I can explain this empirical model in a better way. So the idea is like this. Like we say that we have this functor. We say that we have this functor. Instead, like to look at the scenarios like this, we can look at this functor from contravariant functor to set. Yeah, this gives me the outcome, the functor of outcomes. And here it's give me what is the measurements space. Yeah. You know, if we have a functor to set, we have such a construction called the category of element. Like the category of element, if we have in general, I have some functor from C, even it's contravariant or variant factor anyway. So we have a category of element which say like let's like put all the information in some category. Okay, what we can do, like we can like for every elements in this category, the category of element, let's call it like this element of F. What is this category element of F in terms of objects? Like this will be objects, this will be C, and then I will get by C F, applying F on C on this C, this is C in this category object here. I have F of C, right? F of C is a set. So we will take one object like this, also object. Like we take C and all, like instead of seeing this, we take every C and with object, one object. Like let's say FC is x1, x2, x3. So C give me three objects in this category: Cx1, Cx2, Cx3. Okay, give me three objects in this category in terms of object. So every object can give many objects. It's how much we have in this in FC of this. So this one X in FC. So this is how it's look like object in general. And morphisms in this category, it's okay. It depends. It's contra or not contra. Like let's do it for contra. Like, let's say from the opposite. So morphism, it's a morphism from C to D, like, and here some object for this, and here some object of this. But it's not like, okay, what is this? It's some morphisms from C to D. This is morphism from C to D, but morphism from C to D induce morphism from, because it's contra, so from here to here. So actually this will be, maybe I will write here X, this one X, like let's say, which is someone inside. Yeah, where is it? It's not working here, sorry. X like here. And this will be the image of this, okay? Okay, so it depends, it's contra or not contra, like let's say from the opposite. So morphism, it's a morphism from C to D. This is morphism from C to D induce morphism from here to here. So actually this will be, maybe I will write here X, this one X, like let's say, which is someone inside. Yeah, where is it? It's not working here, sorry. X like here. So this is how morphism, like we really like make everything's like, you know, what we did, like this is, it's this functor, it's written in some way, functor, general functor. We take all the object, all the morphism, everyone with everyone, even like we write here exactly the object that is, it's in the opposite direction because it's contravariant functor. But this how it's like only morphism and some x inside where this x inside FD. Okay, so we put every object and one element inside the set that corresponding to this object. Even for morphism, we set exactly like it's nothing. Like we said, we put here exactly the one that it's going to this one. Yeah, it's like this. Okay, this give us a category. Like we like put this like this. This give us a category. But this category is, of course, it's have this projection functor to the so of this, what we call it C, right? The category C, right? Like every element C, X, it's called C. So let's do this for in this for this functor, and let's say what we get here if we're doing this for this functor. This construction, what it's given. So in fact, it's give me, like, let's say, let's start by the vertices. Like we have some vertices here. If I have vertex, and then we have the outcome of this vertex. I called it V because I don't want to use X like it's use it for other. Yeah, sorry. And here it's a very, and what something here. What is this? This is actually the OV. Sorry, this one is OV. Yeah, OV. So, and something here in OV, like let's call it A. Okay, some outcome. So measurement and some outcome. Yeah, this is measurement, some vertex, measurement. And here corresponding outcome. Yeah. Yeah, for this. So, and let's look at this map, at this functor that we have, the functors that we took. So here we will have the C, this, which actually like the same as sigma, right? We can think about this as a sigma, as our complex. So for every vertex here, for every vertex inside this, up to this will be all the outcome, like V, A, V, B, it's depends how many outcomes, all the outcomes of this, yeah? So will be up to every vertex. And if we take sigma, so will give me, let's say sigma is V UW, yeah? So then it will give me here some vector actually, A, inside where? Inside this of sigma, which is what it's mean. It's mean OU AV cross OU cross OW, yeah? So like, let me write down. So if I have some sigma, and sigma is a triangle, it's have 3 vertices, sigma is a triangle. So it will give me for this, like, okay, up to this, we know that all the outcomes of this, up to this is all the outcome of this, and up to this is all the outcome of this. Let's say I have only 2 outcome. And it's give me like every possible, like some many triangles here, like one can, like this one, for example, will be there, yeah, up to this. There is other, like every that I can do a triangle. So here is the context, and here all the possible outcome for this context, right? Up to this in the same shape. Yeah, we see in the same shape, like triangle, triangle up. Yeah, it's taking the shape of the geometrically is taking the shape of the context, right? If this triangle is triangle, that's sorry. Yeah, you see now. Yeah, so this is what we have actually, and so let's go to this. Like, let's doing the following. Instead of looking at this functor, actually inside this functor there hidden some properties. Like this is not any fun, but anyway, like this functor we have that give me from the standards, we the functor, but we can, okay, this is standard scenario. We can all the information here in this functor, but then we going and put all the information inside this functor, the category of element of this, so element of this, and here we will have okay, this one. We will call this the bundle that corresponding to, I think this is the notation we use in the paper. Yeah. Okay, so we will use this, and but actually this will be not only a functor, this will be a simplicial. One can check that this gives us a simplicial complex map. Okay, like this will be also simplicial complex, not only category. Because it's coming in the beginning from, so one can check it. Simplicial complex, and so here we have up a simplicial complex. How I wrote here? Yeah, I wrote here. Yeah. So we actually used this notation for this. Yeah. Okay. So we have this. But one can think, okay, like there is some properties for this one. There is some properties, important property. Like, for example, one obvious property that is surjective, right? Because for every sigma here, there is some outcomes for this, right? Like this is not empty. Like this one, it's not empty. Because at the beginning, maybe I didn't say like this one, it's not empty. Maybe I didn't say when I like outcome, it's not empty. Yeah, I didn't mention it before, but right, it's not empty. So this is surjective actually. First of all, like let's write the properties of this. Yeah, from this map, simplicial complex map. What is the property? First of all, surjective. It's obvious. Yeah. Surjective. The other things actually for this map, we have something like this. Like if I have, let's back here, like if I have here, let's say some sigma, like let's say from V to U, okay? But this inside something like W, sigma W. And if I found some outcomes for this too, yeah, let's say I found for this, like let A be that corresponding to this, then I can extend this actually, like, and this one inside this, okay? Then I can extend, always I can extend this. Like I can find, because I can find one for this, yeah, such that this one down to all of this, okay? Yeah. Because we need this when we talking about, like we need to do measure what we restrict ourselves to this, so everything's need to be extended like to something if really the context here can extend like W with us, so this got this outcome, but this outcome can extend to another one and to be outcome of this. Okay, so this is an important property. We will call it locally surjective. Yeah, you see, like it's locally surjective. It's kind of surjective, right? We have something in the pre-image, but it's called locally surjective. So let's me write it in a good way, like if we have this sigma from, let's call it from gamma to sigma, okay? Let's say it's from gamma to sigma. So what we say, like for every sigma inside something bigger, if f of some tau going to sigma, then we have tau inside this, such that it's going to sigma, right? Sigma prime, yeah. Yeah. This is called locally surjective. The other things actually we see, like we don't have any in up, if we going up, like they really it's a bundle, like we don't have any between the same outcomes. Like if this is this one have outcomes, so we don't, it's not in the simplex, like we don't have any edge here between two outcomes for the same measurement, right? We don't have this. So of course, like, because why we need this is not in the same context. We don't need this. Yeah. So 3. But we will see later why it's helpful, this property, to do the theory. And 3, so it's what we call discrete over vertices. Like over vertices, there is discrete, not connected together. Yeah, the things is discrete over over vertices. That mean if of some two vertices, let's say A and B, going to the same one, then A and B not it's not in gamma, yeah. So it's not a simplex, yeah, not forms. Yeah. So this is a property, and now, as always, people doing, they said, okay, let's work with the property. Why to define its, yeah, by this abstraction that we're doing. So here is the definition. A bundle scenario is simplicial complex map, or simplicial map between simplicial complexes. Yeah. That's satisfying. Uh, 1, 2, 3. Yeah, 1, 2, 3. I mean, it's like all this property. Yeah, and really we can look at this as a scenario, like when we know in our mind, like that all the up is a corresponding outcome for everything, and they match, as because this is a simplicial complex map. It's preserves the structure. Yeah. So we have this, and then what I want now we can talk actually about the bundle the definition of empirical model, how it's act on empirical model. But before I need to take about morphism here, how we can do morphism here, which we think that it's easier than what done before, okay, by moving to this. Of course, like this is generalization, what we have before, what we had before, but it's really generalization, like, because some, like, for example, I can have this example of, let's say, this is my sigma, and gamma is this, and just a minute. Like even this, you see, like this one, it's enough. I think you understand what I wrote. No, I don't understand. Sorry. Maybe I can write it here and here. Yeah, here is the out for this triangles. Everyone have outcomes. Like, I can use it's better if I'm using, yeah, this is one vertex, and here there is other vertex. This colors. This is the vertex for this, and this is the vertices. It's black of this one. Yeah. So here we have a triangle. This is sigma, is a triangle, and up to this there is outcome. Okay. And there is only this three triangle. Okay. This is like this is gamma. You know what I mean? Like there is six vertices, and there is like three edges like this. So this actually have all the surjective. Of course, it's surjective. It's locally surjective. The property of locally surjective, there is no problem with this. One can check that it's really locally surjective. It's not like there is nothing here. And no, like we don't have any edges between the two. Yeah. Like we don't have edge between this red and this. Yeah. So this, for example, it's a bundle scenario, but it's not coming from, not from standard scenario, right? Scenario. Yeah. So it's really generalization. But why it's flexible, we think, in terms of
Aziz,
morphisms?
so the reason it doesn't come from a standard scenario, maybe just to clarify, we need all the possible edges and stuff, right? That's
you can have, what if it's coming from standard scenario? So you have sigma, the same sigma it will be, but then you have this to be this one, right? What we called, or sigma, I don't know, this one, the gamma, right? The gamma should be, but the element. But when we take the element, like we take, like if this one, there should be some edge between this, right? And between this and between this. Yeah, but we don't need here. Yeah. Yeah. It's between every two vertices here, it should be some edge by definition, if we back to the definition. And it's not like this here. Yeah, one can put many examples like this. Yeah. So how we can define morphism here? So morphism between two bundle scenario, like let's say this is a bundle scenario, and this is another bundle scenario. Why I write in here, we will see. So morphism, it's one from here to here. Like this is a relation map, but here is the problem. Like how we can, we want here simplicial map from here to here, right? We need simplicial map from here. And here is a solution actually. The solution for this is there is what called the nerve. Okay, we will back to this again, but for now, I need to define the nerve functor from simplicial complexes to simplicial complexes, which is actually a monad even. on simplicial complexes. I will define this because what this have properties, this have the following property. Like if we have relation, simplicial relation from to this, we can replace it by a map from this to the nerve. Okay. Okay, we'll talk about the nerve. Okay, so what we're doing actually here, I will explain what this means. So we have a map to the nerve of this. We apply the nerve on all of this in order to get simplicial relation. This map is exactly simplicial relation. And then actually what we will take here, we will take the pullback of this. Actually, pullback in simplicial complex not always we have, but in this case we have because of the properties. This pullback, it's right because of the properties. I think it's because of the district over vertices. I'm not sure. Yeah, I should back to this. I think this is only the properties that we need in order to be a pullback. Because if this is also discrete over vertices, then the nerve of this will be discrete over vertices, and then we have like some construction for the pullback. So we have the pullback here. What is the pullback give me here? Actually, it's give me what we had before. If you remember, is the natural, like it's give me something here, like every x here, and some relation, like some outcomes here that going to the pi x of this, right? So we had before, so pi x of this. And so we have this, what we had before, if you remember, is that we have all the outcomes of this. That what it was something like this. Pi x every y and pi x, the outcomes of this we have here. Actually, in fact, this is what we have here in the pullback, the corresponding to this, the one that going to x, this one. And we have a map from this to what? To the outcomes of this. Let's call it O. Yeah. So really, like there is a map from here to here. So there is two things, like one, this relation that we can use this nerve construction. We can do this as only a map, simplicial complex map. And this also a map, another kind of maps, alpha, also simplicial complex map, but it means the pullback. The pullback because it's give me exactly when we do like this, like everything that match what we say, like exactly this one. And if you back, this is exactly what we had when we like we have many maps like this that are good together. Many maps, we have many maps like this that are compatible together. And you, if you remember, what makes it the compatibility compatible according what is the map down? It's sigma prime, right? You remember, like this one. If we remember back, we did this and we say like this is compatible under like the simplicial structure of sigma. So really we have some generalization, like if we back and if this is f and this is g, it's coming from some standard, so it's the same information here. We have the same information. So in general, how we define it? In general, as we say, like we have a map from F to G is morphism. So morphism, I don't need to morphism. Between bundle scenario is two things. There is this one, this map pi, which is pi from the sigma to nerve of this nerve of sigma. And another map alpha, which is from the pullback of this. So maybe, yeah, the diagram show us everything. So like, let's say the diagram is like this. This is nerve of, yeah. And here is pi. And we take the pullback of this and the map alpha to this that make, of course, the diagram commute. Yeah, here pullback, yeah. And this is gamma prime, yeah. So this is alpha like this, yeah. This is two lines. Yeah, so this is actually, I think good that we put it everything, all the outcome up. This make it like the same. You see, like not natural map as before. we'll see later, like really that this is more flexible language when we extend this. Yeah. When we extend this to bundled scenario instead of standard scenario. What I want to explain to you, what is this nerve actually? This nerve, it's given like if I have some simplicial complex, the nerve of this simplicial complex, it will be new simplicial complex. What happened to this? Just a minute, sorry. Now it's a new simplicial complex. Where is the vertices of this? Is exactly the simplexes of this, okay? The vertices of this is exactly simplices on sigma. And some simplex, it's looking like this, like some simplex in sigma, something like this. It's a set of simplexes, so that like all of them are inside sigma, even the union for them. I don't need this to write like, okay, it's because it's like if the union of them are in sigma, so it's enough. Yeah, this is what I need. Yeah, the union of them such that the union of them in sigma. Yeah. And really the good thing is that there is one-to-one corresponding between relation, like relation, simplicial relation, sorry, what we defined before. Simplicial relations is the same as morphism. Simplicial relation, let's say from here, it's the same as morphisms, simplicial morphism from this to the nerve. Yeah. In fact, this nerve is a monad. So it's a good exercise to see what is the unit and the multiplication of this monad. And there is another important thing actually that this, if we define this category, if we define the category where it's the object are morphisms, are simplicial complexes, like with discrete over vertices, we need this property. And we define the morphism between two to be only the pullback, like morphism from F to G is pullback square like this. Yeah, this morphism from F and G. Then actually this nerve will be a commonad on this category. Like this nerve also act on this square, like preserve pullback square, but it will be a commonad, not a monad. Like this have co-unit, not unit. Yeah, like this will be the co-unit of this will be coming from the unit of the other one. Like it will be the co-unit of this will be this one. So we see like it's the opposite, like because this map in this direction. Yeah. So this will be the co-unit, like the unit of nerve, like this will be the co-unit of this one. And as exercise is good to know what is really the multiplication here, the co-multiplication. When we know the co-multiplication of the other one, yeah, what is here? Sorry, gamma, yeah. So nerve is the co-unit of this category. And then really this can give us the how we can compose there. So the co-composition, because we have actually in our, like, let me write it again. Why is this helpful? Because actually what we have this morphism between bundle scenario with something like this, we said. Right, like here sigma, right? And here some j, and here alpha, and here the pullback, yeah. And right. let's say we have, this is from F to G. This is a map from F to G. Let's say we have a map from G to H. So it's mean we have this beta, let's say here is a pullback of this. Anyway, yeah, so how we can compose, yeah? I need to explain to you how to compose and to get at the end map from F to H. Let's say this is phi, this is phi 1, phi 2, yeah? So here we see, like we first of all compose this square. So this is square, if we think a little bit, because we said that the nerve is a commonoid in pullback square, like when the morphism are the bundle scenarios and even discrete over vertices enough, and like maps is this pullback square. So this act on this, say commonoid on this. So we have this morphism. We can think about this as a Cook-Kleisley morphism. Cook-Kleisley morphism. Yeah, this one. And this one. So the composition, like here is the things, like instead of what we base composition between the functor, here we will have a composition between these two square, and this will give me the Cook-Kleisley composition between the square. This will give me a new square. Right, see it? This will give me new square. So by 2, I think I need to start. Yeah, it's a cosine. This will give me new square from the nerve F here. Yeah, new square. And then we will have here another composition. So we can explain how this is official, but I prefer we will do the same construction when we go into the simplicial version of this, the simplicial sets version, this, which we will not have this nerve without this the nerve. This also will be some advantage of the simplicial approach. And also we will show how we can do this in some categorical way next time. So I will not explain. One can imagine how it's look like, because actually one of them have to act on one in order to get this this one. You can see like it's explained in the paper, I will explain, but then later we'll find some categorical way to do this. Really, it's nicer. So which we'll explain next time. So let me only, I want for a question, I want only to ask you. Yeah, I have something to say about how we define empirical model now. But yeah, let me first of all ask you if you have questions.
Hi, Aziz.
Hi,
Okay, yeah, well, I don't have any question. I have a question, but not directly related to bundles. I have a question in mind that maybe I can ask at the end of your talk, because it's not directly related to bundles. It's related to the nerve.
Yeah.
But anyways, okay, yeah. So maybe if there are any questions, yeah. So are you going to talk about? Okay, so
Maybe empirical model over this, the end of this, I mean,
oh wait, we
to
haven't discussed
define
the push forward, right? That's
what?
oh, I see. We haven't discussed the push forward along morphisms, right? So
Yeah, because it's something like the same as later. The push forward of this, yeah, I didn't discuss also how we did the push forward, but it's right, just a minute. Yeah. Yeah, I will do this because it's the same idea like later with
yeah,
the
that's
with
fine
the
if you
simplification.
wanna
Yeah, I will do
go
this
on to
later.
next
Yeah,
time.
yeah. Maybe next time we will do this. But let me just, because it's a little bit here different, the empirical model, how we can define empirical model over this. So in fact, like we say that there is, this is actually new, I didn't notice this before, but it's in fact that we say that if we have this functor, right, from what it was, yeah, sorry. This functor, was right from this to this, yeah. Then we got this bundle scenario, right? But in fact, we have also, like for every bundle scenario, we will get functor, yeah. How we get this functor? By like new functor, I can call this f minus 1 from this to set. So it's give me for every sigma here, f minus 1 of sigma, like the outcomes of this, okay? And it's functor really because actually the district over vertices, this property, all the property, so the property of bundle surjectivity we need here, like it's make that if I have sigma inside, then we will get some map from this to this unique map, yeah, because we can say in unique way, yeah. So this is because of the properties we get. One can think about this, why it's true. This is by the properties we have. So really we have a functor like this also here. And now it's the same, like after getting this functor, we can do the same and applying this functor, applying D on this functor, composing with D, and the limit of this will be the empirical model of F. Yeah, we can define it this way. The empirical model. It's a little bit different in the paper because we didn't know that this is functor, but it's actually functor, this one, F minus 1, yeah.
Oh, yes, I see. Yeah, so I actually have a, are you finished, Aziz? If so, maybe I will ask a question. Are you able to hear?
Yeah.
Okay. Yeah,
I'm finished. Yeah, I finished.
I have a question. So, yeah, this functor you just defined, which doesn't appear in the paper. So the notion of these bundles of complexes, simplicial complexes, yeah, we discussed this before, right? It's not very standard, but the discrete over vertices condition, it just sounds a bit, I mean, it's almost, I haven't checked it, but maybe you have checked it. Is there any connection here to these discrete vibrations, right? So on the top arrow, you're going from a functor to something like a Grothendieck construction, right? So the top functor. And the other
this is category of element, right?
Right to left, right? There is a standard construction, like the inverse of the Grothendieck construction, right? There's that, and then you get equivalence of categories. Is the discrete vertices condition similar to?
It's not really like this is more like this category have more. It's not equivalence of categories. These functors give me like because this is more have more things. I think it's not equivalence of category even if by object, right? Like it's something I think this is a section of this. Like in one way you can get what you have. Like if you go like this, if we going like this and back, it's the identity.
But the other way is not, right? You get something larger.
No, the other way you can't get because if you start from something that we start before, right? Like
oh, I see. Okay.
If you start like I showed that there's something here that it's not coming from some
Yeah. Okay. But okay. So if you go from right to left and then come back to right, you get something larger. Is that because you want to connect all the things, right? Okay. But yeah, I really find this definition interesting. And doesn't appear elsewhere. It's just interesting.
This have some properties. Maybe if we construct as to some properties of this, not something that coming from standard, like this have also some properties. This functor.
That functor.
Yeah, maybe this then it will be equivalent, as you said. If we not like coming from standard, if we just only say this with his property, this functor with his properties. It's written somewhere in this paradox, strong contextuality paradox, and things they say some property for this functor. Yeah, they are.
Oh, I see. But if you take, wait. Oh, you're right. Okay, so those functors, they're just EOs. They're not arbitrary functors, though, right? So I just
no, the one that came from some standard, right? But
I see. But if you, Sorry. I think my question was more of on the left-hand side, we should have arbitrary functors, right? And on the
Yeah,
right-hand
arbitrary
side,
functor, we need to write the properties of this. Yeah, I think then it's equivalent. I
yeah,
guess.
but I'm asking kind of the opposite direction rather than finding just just relaxing the left-hand side to arbitrary functors and then going from left to right by Grothendieck construction. So do you hit these discrete over vertices kind of map? And I think you should get some sort of discrete vibrations. Maybe the discrete vibrations is the notion that is corresponding to discrete vertices. Maybe that's worth checking.
Yeah. By the way, here it's not true if this is any simplicial complex. Of course, like this is not defined, not well defined. This is well defined because this is over vertex and surjective, and at least these two properties. Maybe we need the third properties. I forgot. Yeah, but at least these two properties we need.
Okay. All right. Any other questions for Aziz? Okay. Then let's thank Aziz. Thank you very much.
Thank you.
Okay.
Okay. So